The paper introduces ALO-VC, a novel any-to-any low-latency one-shot voice conversion system that utilizes phonetic posteriorgrams, PPGs, for high-quality causal conversion. This system is presented in two versions: ALO-VC-R, which employs a pre-trained D-vector speaker encoder, and ALO-VC-E, which enhances performance with the ECAPA-TDNN speaker encoder. These systems require only a 47.5 milliseconds lookahead, making them suitable for real-time applications. ALO-VC systems contain fewer parameters than VQMI-VC, with 8.3 million parameters, excluding the speaker encoder. Experimental results show that both ALO-VC-R and ALO-VC-E outperform VQMI-VC in terms of speech naturalness and speaker similarity on the VCTK dataset and two out-of-domain unseen speech datasets. They also narrow the performance gap between low-latency one-shot VC systems and diffusion-based one-shot VC systems, achieving comparable performance to non-causal systems on datasets other than VCTK. The paper begins by summarizing the state-of-the-art low-latency VC systems, then details the architecture of the proposed ALO-VC systems. The experimental results are presented, demonstrating the efficacy of the proposed approach. The paper contributes to the development of real-time, low-latency voice conversion technology with potential applications in various fields. This section of the research paper delves into the related work in low-latency voice conversion systems and the proposed methods for achieving a novel any-to-any low-latency one-shot voice conversion system. The authors present two versions of their system, ALO-VC-R and ALO-VC-E, which utilize different speaker encoders. The paper first reviews existing low-latency real-time non-parallel voice conversion (LLRTVC) framework, which can perform many-to-many voice conversion with a 0.87-0.95 real-time factor (RTF) when deployed on a single CPU core. It also discusses the use of LPC-net, a state-of-the-art low-latency neural vocoder, to generate high-quality waveform using only 30 milliseconds future lookahead. The proposed system consists of 5 components: an acoustic model, a pitch extractor, a speaker encoder, a conversion model, and LPC-net. The acoustic model is designed based on the conformer architecture but without multi-head attention layers to minimize parameters and inference latency. It extracts 512 dPPGs representation from the source utterance and is trained using cross-entropy loss between the ground truth phoneme alignments and the output from the acoustic model. The speaker encoder component utilizes pre-trained D-vector and ECAPA-TDNN models to obtain speaker embeddings. Two versions of the ALO-VC system are proposed based on these speaker encoders: ALO-VC-R with a D-vector speaker encoder and ALO-VC-E with ECAPA-TDNN. The conversion model is responsible for generating converted 18-dimensional Barkscale Kepstrel coefficients, VSCCs, as well as converted pitch and voiced, unvoiced flag, VUF, for LPC-net to synthesize the converted speech. The model includes a pitch predictor, 2 positional encoding modules, time-distributed fully connected layers, and a 2-layer transformer decoder. The architecture and training of the conversion model are pivotal components in bridging the performance gap between low-latency voice conversion (VC) systems and state-of-the-art non-causal VC systems. This is achieved through the utilization of Kepstrel coefficients, pitch, and AC for voiced, unvoiced flags, which play a crucial role in enhancing the accuracy and efficiency of the model. Fine-tuning the LPC-net for each gender is an essential step in the process, as it allows for gender-specific adjustments that can significantly improve the quality of the output. The experimental setup involves various datasets, model configurations, and training details, all designed to optimize the performance of the VC system. In terms of datasets, the selection and preparation of high-quality data are critical for effective model training. This includes not only the quantity but also the diversity of the data, ensuring that the model is exposed to a wide range of voices, accents, and speaking styles. Model configurations are another key aspect of the experimental setup, as they determine the structure and capabilities of the VC system. By carefully designing the model architecture, researchers can balance complexity, computational requirements, and performance, ultimately leading to a more efficient and accurate VC system. Training details, such as the choice of optimizer, loss function, and training schedule, also have a significant impact on the model's performance. These decisions must be made with careful consideration of the trade-offs between training time, model convergence, and overall accuracy. The ultimate goal of this research is to reduce the performance gap between low-latency VC systems and state-of-the-art non-causal VC systems. By leveraging advanced techniques like Kepstrel coefficients, pitch, and AC for voiced, unvoiced flags, fine-tuning the LPC net for each gender, and meticulously designing the experimental setup, researchers aim to create a more efficient and accurate VC system that can meet the demands of real-time applications while maintaining high-quality output. The experimental results and analysis of the proposed voice conversion systems, ALO-VC-R and ALO-VC-E, are presented. In a subjective test on the VCTK dataset, participants rated the speech naturalness and speaker similarity, showing that ALO-VC-R and ALO-VC-E outperform VQMI-VC and DIF-VC in both aspects. Objective tests on the Libri speech dataset demonstrate that the proposed systems outperform VQMI-VC in quality and speaker similarity. Additionally, real-time factors and latency measurements are provided, indicating that the systems can be used in real-time applications with a latency of 55 ms. The summary emphasizes the effectiveness of the pitch conversion method and the use of PPGs representation in achieving better performance. Please provide the transcript that needs to be refined, and I'll transform it into a concise, technically accurate summary suitable for voiceover narration, following the guidelines you provided. I'll maintain the technical accuracy and depth of the content, explain key terms and concepts with precision and clarity, and highlight novel ideas, significant findings, and important arguments presented in the original text.